So the next presenter is Ariana Osman. Yes, so Ariana is from the University of the West Indies in Trinidad and Tobago, and her talk is about the changing clinoform architecture of the Paleo-Orinoco Late Miocene Cruse formation in Trinidad. So it's an history of the eustatic sea level changes and the interaction with the tectonics setting.
Yes, thank you so much for the introduction. So you already heard the title of my talk. This talk, one second. Yeah, today's talk, I just want to show you how we constructed clinoforms using well logs for the first clastic wedge of the Paleo-Orinoco that was actually deposited on Trinidad. So I just wanted to highlight that although this area has been extensively studied and also drilled, the large amount of tectonic deformation has been really difficult to construct clinoforms from either seismic or outcrop data onshore. So we try and show this, and then we look at the changing trajectories on the clinoforms built and understand if it's actually impacting the regime of the delta. So just to introduce clinoforms for those of us who are a little less familiar, is that clinoforms themselves are sort of snapshots in time of a bathymetric profile. So they show us top set, foreset, and bottom set. And these have sort of different scales. We are looking at continental margin scale clinoforms. And between each one of these mapped clinoform boundaries is what they call the clinothem. And this is a sediment prism at the basin margin that actually constructs the shelf margin through repeated regressions and then subsequent transgressions. Now, the Orinoco Delta in the Trinidad area is built on probably more than 100 of these regressive, transgressive cycles. And we think these occur on likely fourth order timescales. Now, clinoforms themselves are really quite significant because they help us understand both paleo shorelines as well as water depth. And if we follow the sort of shelf edge trajectory or shelf slope break at each successive margin and follow these systems, we can understand different trajectory changes. And these trajectory changes can be linked to varying supply and accommodation systems. So generally, when you see a flat trajectory, this represents more limited accommodation, while rising trajectories generally indicate increased accommodation. So in a sense, trajectory analysis really complements system tracks analysis, and it's become quite a significant or method being used to understand whether we get bypass to deep water. A sort of shelf margin, dispersal on a shelf margin, and accretion is one of the main methods by which we get sediment being transported further, or sands being transported to the deep water. Just as a sort of side note though, delta regime is also really important for how sediments are dispersed beyond the shelf edge. And we should not forget that regime is very dynamic. So as deltas sort of prograde across the shelf margin through regression, they can actually change whether they're wave tide or fluvial dominated. In general, we think that as shelf edge deltas, or as deltas approach the shelf edge, they tend to become more wave dominant as they enter sort of more open waters. And wave-dominated deltas tend to store more sediment on the shelf than river or tide-dominated systems. So just to sort of highlight the study area, Trinidad is located on the image on the northern boundary of South America, located here. Now, until the Oligocene, Trinidad was largely under passive margin conditions, and across the entire margin of boundary of South America was impacted through a series of diachronous phases of tectonics. First, you had passive margin phase, and as the Caribbean plate continually migrated eastwards, you underwent oblique collision followed by a series of transpression and transtension. So in the Trinidad area, we weren't really affected by the Caribbean plate until the Middle Oligocene, all the way up to the Plio-Pleistocene. Of significance, though, is that as the Caribbean plate migrated upwards, it created a series of uplifts on that northern boundary of South America, and this rerouted the major Orinoco Delta system that was once north going to its current east-west transit. So in In Trinidad here, the study area is within the southern basin. It's essentially a northeast to southwest open-ended trending foreland basin. And however, during Cruse deposition, which is our first clastic wedge within the basin, it's not impacted yet, or it does not yet have defined boundaries on the basin. So these main sort of thrust sheets were not emergent. They likely during this time, there was a series of active blind thrusts that were affecting our margin. The actual southern basin is filled by 4 main clastic wedges that started in the latest Miocene up to the Pleistocene. Each of these clastic wedges is bounded by a major flooding surface. So today we'll just be looking at the Cruse formation, which has an upper and lower member, whereby the upper Cruse is defined by the top set of the shelf margin and the lower Cruse represents the slope and deeper water sediments. So I just want you to understand how I went about mapping the clinoforms or clinoforms. We're within the study area, within the red polygon. Of importance to note is during this time, we think that they had at least 2 blind thrusts that were active, as well as this sort of Los Bajos fault, which is related to likely transpression that's occurring across the margin. So within the study area, we had 58 wells and 3 main outcrops located on the south coast. Now, we have in the wells, you can recognize clinoforms from the transition from really sandy top sets to a large muddy interval, which represent our foresets, and then finally our bottom sets. We picked the top and base of our entire formation. And then to construct individual clinoforms, what we did is we correlated our regressive transgressive cycles within the top sets using flooding surfaces, and then extended it further basinward into the muddy interval. Upon doing this, we use a semi-model-based approach where we understand that the current slope or delta slope for the main clinoforms would be between 1 and 4 degrees. The modern Orinoco Delta has a slope of about 2.5 degrees. So we use this sort of model-based approach, as well as subtle well characteristics to carry it across to the basin floor. So for our clinoform description, in yellow, you can see a sort of built Cruse clinoform set. This represents long-term progradation of the margin before being capped by the main flooding or main transgression, which the well set is data set is hung on. Now, if you observe the individual top sets where these correlation lines build through, these represent individual regressive and transgressive cycles. For each regressive and transgressive cycle, each regression moves one step probably further basinwards before the subsequent transgression. This means the top sets are actually offset through time. So at any one well, we may not have the same number of top sets actually being visualized. So for example, in these G wells towards the west, they have far more top sets being preserved than what's further to the west, which represents much younger clinoform sets. Now, the average slope for our clinoforms is about 2.5 degrees, and they taper towards east of the margin. From our most complete oldest clinoform, we can see the clinoform height is about 750 meters. Now, this is undecompacted, but it represents a potential water depth of 750 meters. However, subsequent younger clinoforms have much smaller heights of only 450 meters. This could represent the progressive filling of accommodation as the system progrades towards the east. Now, if we actually stack our shelf edges with time through these constructed clinoforms, we can begin to understand sort of changes with time. So in our youngest clinoform, these are much further towards the west. And then suddenly there's a jump forward where our shorelines or shelf edges sort of make a rapid forward progradation through all the way actually up to C21, where they hover around the same place, except for C16 that appears to the shoreline actually slightly backsteps before the youngest set of clinoforms actually prograde again on the system. Now, what we've done is we've linked our data set here. So this is within our study area to a well that's located in a proximal location. And this helps us construct or sort of confirm the shelf margin width being about 45 degrees. So we can correlate this well to our data set, helping us identify the shelf width at this time. Now, this shelf width is actually much smaller than our Pleistocene or younger Orinoco clastic wedges on Trinidad. And this could be because of the slightly warmer times during the Miocene, whereby sea level rise and falls may be much smaller than the Pleistocene times. So when we actually map the shelf edges within the region, we can see the long-term progradational trends. So you can see in our oldest clinoforms, C10 to C13, they make a sort of progressive flat trajectory or sort of strong progradation before being more aggradational, so stacking or rising trajectory before flat again. Now, this trend is likely not related to eustatic changes, whereby each regressive, transgressive, so each individual clinoform would represent a eustatic change. However, the longer-term trend could be related to, or signal tectonic impacts. Now, during the Middle Miocene, which was before the arrival of the Cruse Delta system, really signified the culmination of oblique collision of the Caribbean plate with the South American plate. And sort of this time progressive thrust front load may have begun to impact the Trinidad area during this time, increasing accommodation. And this could account for possibly some of our rising trajectories, or it also indicate the onset of transtension within the basin, which was common during oblique collisional times. Oblique collisional times. And this could also account for this sort of major transgression that we observe at C16. And quite interestingly, this also correlates quite well to our well from literature, where you actually see a major sort of muddy interval also transgressive during this time. Now, the Cruse clinoform growth, you can also observe this on a regional scale. So this is our study area here, whereby the Cruse shelf edge actually maps with what's been mapped offshore in the Trinidad Columbus Channel and in the Columbus Basin. This is a seismic line E to E prime, and you can also see for the younger shelf edges, they also maintain this flat rising, flat trajectory. So it's likely that the entire Orinoco margin on the Trinidad area was impacted by probably a series of tectonic pulses, probably of transtension and transpression, resulting in these changing trajectories. Now, of course, as I mentioned earlier, what's important to these trajectory changes is it could also be used maybe to predict times when more sediment might be moving beyond the shelf edge area rather than being stored on the shelf margin. So in addition to looking at the clinoform framework, we also looked at the sand distribution within these individual clinothems. So we've mapped the sort of net sand distribution from our oldest all the way to the youngest clinothem. So C10 is the oldest and C24 is the youngest. And what you can see is a real preservation of these elongate sort of sand bodies. And integrating these elongate sand bodies with also what we see in outcrop, we assume that this likely had a strong fluvial dominance. However, with time, these systems became more shoreline parallel and potentially represent more wave dominance on our delta. So we look at FA1, which is our shelf margin, our shelf edge, some of the facies from this to illustrate some of the fluvial dominance, as well as some of our deeper water facies. So from Outcrop observations, you can log about 240 meters on the south coast of Trinidad, and these correlate likely to our youngest clinoforms, C22 to C24. And what we see in outcrop, we see this nice coarsening upward, these really nice coarsening upward successions that are down cut by these strong incisions on the shelf, probably likely indicating strong force regression before being infilled by estuary deposits. But of significance today is that you can see strong fluvial evidence on the deltas. We see the preservation of hyperpycnal flows represented by really planar lamination or beds with reverse and normal grading, as seen in figure D. You also see the preservation of strong, lots of lignitic material, as well as the development of mouth bars. Also, you see periods of intermittent biotubation. So you see times where it almost has absolutely no biotubation to then strong biotubation again. And this is common in fluvial dominated deltas, where maybe you get times of flooding on your delta front, which results in very stressed environment, followed by more quiescent times, resulting in more biotubation. So we see apparently strong fluvial evidence on our delta. The other facies I'd like to highlight is associated with some of our oldest clinoform sets outcropping on the south coast of Trinidad, is they actually have deep water deposits, slope channels. Some of the slope channels are formed very far on the lower slope, but we interpret to be on the distal lower slope to the basin floor. And we see actually the development of these sort of fringe deposits. These are assumed to be on sort of the outer edges of lobes, and quite commonly associated with these are hybrid deposits. This is a kind of transition from seeing really nice developed turbidity currents to a sort of transitional or debris type flow. So we see the development of nice TA facies being capped by these convoluted sort of beds with carbonaceous, poorly sorted material with a kind of colli-like appearance. Now, what's significant about this, it means that you're having sort of this lignitic material that is likely being transported from our shelf edge or shelf edge regions into the deep water. This suggests also some sort of fluvial evidence whereby we get coeval channels that can transport sediment through hyperpycnal flows that convert into turbidity currents downslope, bringing this sort of carbonaceous material with it. It could signify this, as well as potential collapse at the shelf edge regions. So there appears to be a strong link between our shelf edge and deep water. So is there a link between fluvial dominance and tectonics? I think that there may be. When we look at the top set sort of sand distribution with time from C13 to C24, in our youngest clinoform sets, we see this elongate finger-like geometry. And we can see in outcrop, we do see fluvial evidence on the delta. Interestingly as well, lots of our fluvial systems appear to align to the Los Bajos fault. So this fault system is probably active and acts as a sort of conduit pathway for our river systems. Notice we mentioned earlier these blind or growing thrusts on our margin. Once the river systems, or we interpret that once the river systems are sort of behind these blind thrusts, they probably have greater fluvial influence. And as the delta progrades past these sort of thrusts, they become more strike elongate, probably signifying higher wave dominance on the system. So it's quite possible that these thrusts are sort of inhibiting or creating an embayment, protecting the delta from very strong wave energy. And this kind of really contrasts to how we classify a lot of our shelf edge deltas on Trinidad, which are much more wave dominant. So in this case, I think the tectonics are strongly influencing also the regime of our delta. So finally, I just wanted to close that if tectonic signals can be separated from eustatic signals on the Orinoco Cruse wedge, I think it can be. I think that we see, as I mentioned just now, you see significant evidence of where our thrust sheets align and sand distribution, it appears to impact it. In addition to that, our changing clinoform trajectories are likely impacted by these changing times of transtension and transpression, and it probably could be mapped through these series of clinoforms. However, it shouldn't be forgotten that really eustatic cycles on the fourth order is probably what every time drives our delta towards the shelf edge through regression and then the subsequent transgression. And one final thought is that our study area is only on a very small portion of the Orinoco system. And if you compare this even to the modern Orinoco system today, it has a sort of bipartite regime with a very wave and then tide dominated. So it could be that we're just looking at such a small segment of the delta, it doesn't give us the full picture of how the delta is behaving when it first arrives on Trinidad. So that's all I have. And if you have any questions, I'll be happy to answer. I'd like to thank Trinity, Petratrin for data, as well as University of the West Indies and the many people who have helped me with this study.
Thank you, Ariana. So I see that there is a person, hand raised, is Caitlin Marsaglia.
Yeah, sure, hello.
Yes. Kathleen, you have your hand raised. Do you have any question? Okay, so I just unmuted you.
You're unmuted now, Kathleen. You can go ahead.
Yes. Okay, so any other question? Okay, I see another person. So it's Marcelo Misoni. Okay, so I don't. Marcelo, okay, I unmute you. You can talk.
Okay, good. Can you hear me?
Sorry. Yes.
Okay, just
clear.
a question. Have you considered paleobathymetry as a possible control also on your progradation rate? I know that paleobathymetry could indeed be controlled by tectonics as well, but maybe not as directly as source of sediment or quantity of sediment, I guess. But if you consider that, you know, in a lot of these cases, you see this great progradation when you have a little accommodation, so in a shallow basin, and then as you go into a deeper basin, you are essentially forced to aggrade. Have you considered that possible control?
Yeah, so in a way I have, but I think I've considered this more for some of the younger clastic wedges. I think that in the case of the southern basin, that this area is, the paleobathymetry might be continually decreasing, and maybe in some parts you might even get climbing clinoform sets where the bottom set starts to climb because of the continual uplift. But I do think it impacts, as you mentioned, as you go further basinward in places that maybe where you don't get decreased accommodation, that this paleobathymetry could actually impact the changing trajectories.
Okay, excellent. Thank you. Great talk.
Yeah, thank you so much.
Any other question?
I have a question, Lillian. I can't figure out how to raise my hand.
It's okay.
So I'm wondering about the nature and extent of soft sediment deformation you see in this system, and if that seems to have any effect on your clinoform morphologies, or if this is a relatively undeformed system.
So in outcrop, you do see quite a lot of soft sediment deformation, but I don't think it impacts each like shelf margin clinoform. It does impact sort of the shelf edge collapse and things like this. You do see that, but it's not impacting, I think, the morphology of the overall clinoforms, at least what I can map from wells. There are certain wells, for example, that are less than 100 feet or 50 feet apart, and some will have sand and some don't. And I think this is due to like shelf edge collapse or sort of onset of deformation or mass transport complex forming on the slope.
Excellent, thank you. And it seems like we've got a question.
Yes, we
Leslie
have
as
one
well.
more person. We have another question also for Tom. So let me just unmute. So we have two questions. One is Tom Pepload,
Okay.
and I just unmute you, Tom. Hello, Tom. Okay. I think Leslie also have a question, so I will.
You hear me?
Yes.
Okay. Ariana. Awesome.
Hello.
So if you go to your map, I'm looking at C22, and then if you go to C20,
Okay,
your
hold on, I'm just
maps,
trying to get that.
your maps are shockingly conservative. Oh my God, I thought I taught you better than that.
This one?
So are your maps, do you feel comfortable extending those slope channels and things basinward, or are you only comfortable just it seems to me like you're going to your last well point and then you're just sort of terminating them right there. And
I agree. I'm not always so so generous. I think that at least from the wells I have,
yeah,
the earliest clinoforms have really nice, thick, well-developed sands.
yeah.
While these skinny ones, I can share these maps, I guess, with you that these are actually contoured as well.
Yeah.
These aren't very thin, and I do wonder if during times of that strong rising trajectory,
Yeah.
on our shelf, if our slope channels and stuff are also slightly more confined. I actually, in my newest data set, I do have a few wells that are further towards the east, and they also don't show very convincing signs of any nice developed slope channels or basin floor deposits that you see in the youngest set. So
you think, do you think those channels really do terminate right there?
I agree. Maybe they don't quite terminate, but I wouldn't say I don't know if they have anything massively sandy at the base. Yeah.
So you
I would say it's more that I'm not sure they're transporting lots of sand.
You're telling me I shouldn't be exploring basinward of that, right?
No, I would be conservative on exploring, or at least being able to predict where nice big fans are. From this section, I wouldn't feel very confident, no.
Is there any way that you would suggest that there's a zone of bypass and that the sands would pick up farther basinward, or do you feel like you really are at the eastern terminus?
That's a really good question. I mean, I don't know in terms of at least for the data set I have, and from anything I've seen on wells or seismic, how much sands are getting to the basin floor. I was actually wondering if you have nice fans, but if they're muddy, just because the amount of sediment that comes off the Orinoco, they say if 2/3 of the sediment is bypassed. In the case of even C10 to C12, you would anticipate to have large sandy bodies, but even in the one outcrop I have and the well logs, it's not convincingly very, very sandy.
Huh.
So I'm not sure. I don't know, but I hope that helps answer your question.
Yeah, we'll have to talk about it some more. Nicely done. Sure.
Okay, thank you. Thank you for the questions.
I have one more question, and it says Ton. Let me just get it. And what he said is, Ariana, do you see evidence of compensation stacking on the slope?
No, I haven't seen any evidence of strong compensational stacking on the slope in the wells, but I don't know if it's as I said, controlled by the data set in terms of how close all of my well spacings are.
Okay, well, great. Thank you very much, Ariana.
Thank you very much. Thanks for having me.
Yes, so we're going to just give a 5-minute break, and I'll see you at 2:45.